the last session. Okay, if not, we'll get going. The screen is visible clearly, right?
Yes.
Yes, sir.
Sir, just one thing from yesterday's on the subjective discussion we had. Is there a difference between checking subjective for vector spaces versus linear transformations?
Not really. What do you mean vector space? For general functions and linear transformations, is that what you have a doubt about?
No, actually, I saw a question in PYQ that speaks specifically about vector spaces. I was wondering whether there's any difference between these two. I mean, if you check vector spaces.
Surjectivity is something that we discuss in the context of a function. Just for a vector space, we don't discuss. It does not make sense to talk about surjectivity just using a vector space. It is generally of a function. So maybe can you tell me what the question is? Exactly what the question is?
Yeah, so there was one vector space that mapped to. We were asked to check if the if it is isomorphic to another vector space, which is R2. So there were options were given, and we were asked to check whether it is isomorphic to another vector space R2.
Yeah, so if it is isomorphic or not, that is just a dimension check.
Actually, okay. You
So
don't need to
yeah, we
check
don't need to
back.
explicitly construct an isomorphism. We just need to guarantee the existence of an isomorphism, which is there once you have the dimensions to be equal.
Correct. Yeah. Okay.
So when it is asked, is one vector space isomorphic to another vector space, it is just another way of asking, are the dimensions equal?
And in that, they had given one of the options was column space. So I wasn't too sure about how
Okay,
that.
the column space may have had dimension 2 then, or whatever. If it was a correct option, then probably column space of some matrix,
Right.
it maybe
Okay,
had
that was not the
dimension 2.
correct option, but yeah, I got a little confused. So anyway, that. So you were
Okay, then
saying
it
that
might
it's
have
not
been
any
it
different.
was a matrix whose column space had dimension other than 2.
Hmm. Yes.
Okay, let's start with the concepts of week 7 and 8. So towards the end, we did see what matrix representation of linear transformation is in week 6. Now, two different matrices can be the matrix of a transformation if you choose different bases, right? So what is the property that sort of unites all these matrices? So this comes to equivalence of matrices. To make this formal, we define what is equivalence of matrices. Two matrices are said to be equivalent if one can be written as, so B can be written as QAP, where Q and P are invertible matrices. If such a expression can be written, then the matrices A and B are said to be equivalent. These need not be square matrices. For the notion of equivalence, we can work with rectangular matrices also in general. But of course, both of these have to have the same order. The matrices A and B have to have the same order, and the orders of Q and P will be uh, Q will have M and P will have N. The matrices Q and P will be square matrices, which are invertible. Invertible meaning square matrices is implicit in it. So this is what it means for two matrices to be equivalent to each other, or one matrix to be equivalent to another. But it is the same as equivalent to each other because it's a symmetric relation. So it is more than a symmetric relation. It's actually an equivalence relation. What is an equivalence relation? It means it is reflexive, transitive, and symmetric. All of this we have discussed in the live sessions in more detail. But what is important is how to check for equivalence. So while the definition says B is equal to QAP is what we need to look for, that is not an easy condition to check, right? You cannot just try to solve for QAP, especially for matrices larger than, even for 2 cross 2 matrices, you can go and check if you'll have 8 variables for Q and variables for P. Even there, it will be a nightmare. So it so happens that there is a far easier way to do it. It is to check the rank. If rank of 2 matrices are the same, then they are equivalent. And it's an if and only if condition. Rank being the same is equivalent to uh, the matrices being equal. The other one is one can be obtained from another using a finite series of row and column operations. The row operations that you use for to get it to REF, the similar things for columns also you can formulate. And if you can get B from A using this, then these are equivalent. To check equivalence, most of the time, you will just be using rank of A is equal to rank of B, wherein you might be given 2 matrices, and there might be some entries missing or some arbitrary entries, and you have to find values such that these two will be equivalent matrices. In that case, all you need to do is bring them both down to their REF or RREF. And then how do you find the rank once you have the REF?
Number of pivots.
Yeah. So a number of pivots have to match. And in that case, they'll be equivalent. Now, for the thing that I was talking about earlier, is the relationship between two matrices of the same transformation with respect to different bases. Now, a matrix of a linear transformation is not something that is specified independent of choice of basis. It is specific to what basis you choose for the domain and the codomain. And if you have a matrix A, which is the matrix of the transformation with respect to basis, ordered basis, whenever I say basis, it'll always be an ordered basis, because when you're writing the matrix of the transformation, the order is important. So ordered basis beta 1 and gamma 1 gives you the matrix A, and the basis beta 2 and gamma 2 give you the matrix B. Then A and B are equivalent. We will not prove it, but it is not a very difficult proof to see that they're equivalent. To show that they're equivalent, what we need to do is rank of A is equal to rank of B, right? But what is the rank of a matrix of a transformation? If you recall from last session.
It's the number of independent variables.
right?
Dimension of
One at a time,
codomain.
please. It's not exactly dimension of the codomain. Rank is related to one of the subspaces associated with the transformation.
Image space.
Yeah. So this is the dimension of the image space. So that is why if you have it to be a full rank matrix, then you'll have surjectivity. Full rank meaning maximum possible. If the rank is equal to the dimension of W, then you'll have surjectivity. So the nullity of the matrix is equal to the dimension of the kernel, and the rank of the matrix is equal to dimension of image. Right? So rank of A is dimension of image of T, and rank of B is also the same. It's I can choose whatever basis that I want. On the other side, the image of T is something that is independent of choice of basis. Image of a transformation is fixed. So those two things are the same. So rank of A is equal to rank of B, and then you'll have equivalence of A and B. But if you want, but here there is more, that you can actually get an expression of the form B is equal to QAP, which was the fundamental definition of uh, equivalence of matrices. In general, when you say these two matrices are equivalent, rank of A is equal to rank of B does prove that statement, but it does not give you the choice of matrices which you can multiply so as to get B from A. But in this case, we actually have an algorithm. How do we do it? In order to get P, we express beta 2 in terms of beta 1. Now, what does that mean? What is beta 2? Beta 2 is a basis. Let's say this is an n-dimensional space and this is an m-dimensional space. So beta 2 is a basis of V, which is an n-dimensional space. Let me call this V1 primes, and beta 1 is this. So what I mean by expressing beta 2 in terms of beta 1 is, if I write V1 prime, this is a vector in V. By definition, this can be written as a linear combination of, let me just write it as P11. Why I'm writing it as P11 will be clear. So on up to Vn1, Vn. This can be written uniquely as a linear combination of VIs, right? VIs are a basis. Beta 1 is a basis. So any vector can be written in terms of beta 1. So I'll just pick all the vectors in beta 2 and write them in terms of beta 1. And this is what I'll call this decomposition I'll use and so on. We can do this up to Vn prime. And these coefficients that you get, P11 up to Pnn, this is what is the matrix that is obtained by expressing one basis in terms of the other. P1n, yes, Pn. So once again, these coefficients are coming as columns. So the coefficients of the first vector expressed in terms of beta 1, that will be your first column. The second one, the coefficients of the second vector will be the second column, and so on up until the nth vector, which will become the nth column. And this is P. And Q is obtained by expressing gamma 1 in terms of gamma 2. So there is a reversal in the way you are expressing it. Beta 2 in terms of beta 1 gives you P, and gamma 1 in terms of gamma 2 gives you Q. We have done examples for the same also in the sessions, in the live sessions for the week. So you can maybe refer to that for an example. Now, what is more particular than equivalence is the notion of similarity. And this is a notion which is valid only for square matrices, where the number of rows and number of columns are the same. So if you have two matrices, two square matrices of the same order n, then they are said to be similar if one can be expressed as P inverse the other times P for some invertible matrix P. In this case, everything has order n. The matrix P is also a square matrix invertible of order n. Everything is a square matrix of order n. Here you don't have QAP. Instead, you have P inverse AP. Like that Q. First of all, in the case of equivalence, that could be the P inverse might not even make sense because it would be a non-square matrix. There it would make sense, but if you have say m cross n over here, your QAP this would be an m order square matrix, this would be an n order square matrix. So P inverse would also be an n order square matrix. So this expression would not make sense then. So, but in this case, everything is okay. And if B is equal to P inverse AP is satisfied for some invertible P, then it is said to be similar. Once again, being similar is an equivalence relation. A is related to A is related to B, A is similar to B implies B is similar to A. And A is similar to B and B is similar to C implies A is similar to C. So that is the definition of an equivalence relation. That also can be checked once again. But in this case, the things that we have studied in the course are not enough to give a simpler way to check similarity, other than in the special case that we will discuss in the next slide. So what we have is necessary conditions. We can have rank, we should have rank, trace, and determinant to be equal if there is similarity. So similarity implies rank is equal, similarity implies trace is equal, similarity implies determinants are equal. So here you can also talk about determinant because we are restricting ourselves to the case of square matrices. But even if all of these quantities are the same, it need not imply similarity. For example, if you have this, this is a very standard example. So you have a rank of A is rank of B, determinant of A is determinant of B. And what was the other thing? Trace. Trace of A is equal to trace of B. A and B are not similar. Geometrically, what does similarity mean? It is not for this session, and right now I don't quite recall also. Maybe at some later point I will. Well, there is something called geometric multiplicity and algebraic multiplicity of eigenvalues and so on. In that, you can use that to connect it with similarity, but we are not discussing that over here.
Okay, sir. Sir, at the end of the session, can you say some resources to look for it?
Okay, I'll see. I don't know if I remember, but I'll check and I'll let you know.
Okay.
Yeah.
So there won't be any questions asking us to prove similarity or asking if it's a similar, if they're
No,
similar or
no.
something, right?
There could be questions of the form, if these things are similar, then what would some unknown value be? Because then you can compare things, right? You can compare determinants and then
Yes. So will they ask us to
compute or
find the
trace.
value of P?
So if it's, suppose you have something like a matrix A has determinant, or let's say trace. If trace of A is 5 and B is a matrix which is similar to A such that B11 is 2, then what is B22? This is a 2 cross 2 matrix, by the way. So this should, what is this? So then this would be 3, right? It has to have the same trace, meaning the sum of all the diagonal entries have to be same. Things like this can be asked. Show that something is similar, will not do.
Okay. So they won't ask you to find the value of P, right?
No, the matrix which we need to get this sort of expression.
Yeah.
So,
In the specific case of matrix representation of the same transformation with respect to different bases, there something can be maybe asked, because there you have an algorithm that we'll discuss now.
Okay. And eigenvalues are also not there, right?
Yeah, it's not a part of the syllabus.
Okay.
so,
Yes.
so in the given example, the matrix A and B are similar.
They are not similar.
So why? Because rank, determinant, and trace are the same, and their size, I mean dimension, is also same.
Yeah, this is what I'm saying, that it is not sufficient to conclude similarity. So
Yes, sir.
to, at least in this case, you can say that it is not similar because what would P inverse BP look like? B is the identity matrix. So P inverse BP will always be B for irrespective of what P you take. So you can't have any matrix similar to the identity matrix other than itself.
Okay. So using this formula, how to check?
How to check what?
How to check matrix is similar or not?
You cannot conclude similarity using the things that we have discussed so far, and that is not something that you will be tested on. You can say this is not similar to this.
Okay.
Or if it is given that it is similar, you find some quantities. That sort of questions can come.
Like if given it is similar, then we have to find the reasons like rank is similar or determinant or trace.
Yeah, you can use that and conclude. See, for rank, you actually require weaker conditions. So similar implies equivalent because similar implies rank is equal. So it is equivalent. So you can compare the ranks, and if you get the missing values there itself, then we are good. If it is a missing value sort of a problem. But otherwise, you can compare determinant and trace. It's not, these are the three quantities that there are potential questions from.
But these properties are satisfying this example, na?
Yeah, so if it is similar, then these quantities need to be equal. If the quantities are equal, that does not imply that they are similar. And this is an example which demonstrates that statement. If A is similar to B, this implies that rank of A is equal to rank, det, and trace are equal. The other implication is not rank, determinant, and trace are equal, does not imply that A is similar to B. Is that fine? Is that clear? All right. So similar to the case of equivalent matrices, the similarity is something that is connected to matrices of the linear transformation in the following way. In this case, we do not consider transformations between two different vector spaces. Suppose we have a linear transformation between the same vector space, like it's a linear transformation from a vector space to itself. These things are also sometimes called operators. So that's why I put this over here. This is not a terminology which is used in the course, so I'll not use it very often. But if it is a linear transformation from V to itself, then I don't need two bases, different bases for the domain and the codomain. I can just pick one basis for V, and I can use it for the domain as well as the codomain. So what is the matrix of such an operation, such a linear transformation? If I take beta and gamma, two different bases for V, and first I get the matrix with respect to beta for both domain and codomain, and then in the second instance I take gamma as the basis for both domain and codomain. Then A is similar to B. Here, yeah, last time we related rank to dimension of the image and said that it is equivalent, but here I don't have a proof for this right now. But the fact is that you can actually obtain the P also in this case. And how do you obtain P? You can just express gamma in terms of beta. And once again, what does expressing gamma in terms of beta mean? You take each element or each vector in the basis gamma, write it as a linear combination of the basis beta using vectors from the basis beta. and then arrange them as columns. So you'll get a n cross n matrix in this case, if everything has a dimension n. And that turns out to be the P. In fact, here you can also say that P inverse, you can, once you have a square matrix P, you can calculate its inverse by doing your cofactor, adjugate, divide by determinant, that procedure. You can also, in this specific case, you can also do by expressing beta in terms of gamma. The matrix that you obtain by expressing gamma in terms of beta is the inverse of the matrix that is obtained by expressing beta in terms of gamma.
But it doesn't really matter. Like we can express either ways, right?
You can do either way, yes. But the matrix that comes over here, you just need to keep in mind that that is gamma in terms of beta. And once you get a square matrix, you can get the inverse just by doing the inverse the usual way. But I'm just saying that this is also something that can be done. I don't know if it is any easier or harder than calculating the inverse of the matrix, but this is one more way to do it.
We can also obtain P by expressing beta in terms of gamma, right?
No, P has to be gamma in terms of beta. There the order matters.
Oh, I thought it's symmetric, right? Like, I mean, when I say symmetric, interchanging it, will it affect something?
Yes, so P and P inverse need not be same. The matrix that you get will not satisfy the property P is equal to P inverse.
Oh,
Need not.
okay.
The matrix that is obtained by expressing gamma in terms of beta, if you call it P, then the matrix that you obtained by expressing beta in terms of gamma is P inverse.
Yeah.
So specific example, if you want, we can take it. We can look at it at the end.
Okay.
Right.
Yeah.
I'll just probably just go back to the notes of the live session for this thing, and I'll show you where those two matrices are not equal.
Okay, sure.
This does not happen in general. In fact, it will almost never happen. P square is equal to identity can happen. Yeah. Now that's about equivalence and similarity of matrices. The next thing is the concept of affine subspaces. This generalizes vector subspaces. This is like translates of vector subspaces, wherein you take a vector subspace and you add a fixed vector to each element of the given vector subspace. The set that you obtain is called a affine subspace. The picture that you have to have in mind is something like this. So if you have this vector space, which is a straight line through the origin, which is a vector, all vector subspaces are either the trivial vector subspace, a line through the origin, or the whole plane for R2. If I translate it using this vector, each of them using this vector, then what I get is a parallel line. So that is what is an affine subspace, at least that is how you see it. And so an affine subspace means there are two things, a vector and a subspace. You add this vector to the subspace, the set of all points that you get is an affine subspace. So it so happens that such an expression of a vector plus a subspace is not unique. The subspace is actually unique, but the vector that you add to the subspace need not be. You can choose any vector from the affine subspace itself, and that will work to express this in that form. Meaning, if L can be written as V1 plus U1, and L can be written as V2 plus U2. Suppose you have two expressions like this. These two as sets are the same. If that happens, then you need to have U1 is equal to U2, but V1 need not be equal to V2. So V1 and V2 have to be in L. That is the only requirement. So the general expression of a vector subspace of an affine subspace is V plus U, where V is in the affine subspace and U is a vector subspace. Now the common examples, okay. So here we have seen translates or addition of a single vector to a line. So what are the other subspaces of R2? The trivial ones.
Origin is zero vector.
Origin and the whole plane. So what happens if I translate the origin? What if I add a single point to the origin?
It will become the single point.
It will be a single point, not necessarily the origin. Whatever vector I use to translate, it will be that single point. And what if I add a vector to all points on the plane? What is the set that I get?
It's again the same whole R2.
It's the whole plane itself. I cannot really go outside that. And anyway, everything will get picked up. So the example, so if for vector subspaces, the exhaustive list is the zero subspace, lies through the origin, and the plane. But for affine subspaces, it is points, lines, and the entire plane. Now the point need not be the origin. The line need not go through the origin. And the entire plane, you cannot really miss the origin there. So these are all the affine subspaces. Once again, over here, one thing to note is that for vector subspaces, we have certain linearity properties. We have closure under vector addition and scalar multiplication. This will, in general, not be true for affine subspaces. If I take some line not passing through the origin, let's say this is y is equal to minus x plus 1. If I have something like 1, 0 and 0, 1. These are points on the line, but its sum is not. 1, 1 is not, or any scale of it is not. Right? So this linearity property need not be satisfied by affine subspaces. And just like the solution to a system of homogeneous equations, homogeneous linear equations, a homogeneous system of linear equations, that was the model space for, or it was one of the prototype examples for vector subspaces. Here, this generalizes to any system of linear equations. But there is one minor subtlety that the solution system to the solutions to a system of linear equations, it might be empty. What is it? What is the term used when it is empty? What is such a system called?
Null specific.
No. When a system of linear equations has no solutions.
Inconsistent.
Yeah, it's an inconsistent system of equations. In that case, the solution set is an empty set. The empty set is not an affine subspace, right? At least it should have at least one point. But if you can guarantee that there is at least one solution, then it is an affine subspace. And the expression of the solution to a system of equations, as we were doing before, like we were always writing it as a vector plus a subspace, right? So in this case, the expression is a particular solution plus the null space. So what is the vector subspace associated to the affine subspace, which is the system of solutions to the system of equations? It is the null space of the matrix. And what vectors can you use to translate so as to get this? You can use any particular solution, any specific solution you can take and translate the null space. What you will get is the set of all equations, which is an affine subspace. Probably there needs to be a point maybe in the previous thing. So dimension of the affine subspace this is a terminology that is used, is the dimension of the associated vector subspace. So here you see you cannot talk about basis, and because you don't have any linearity properties as we know it. Whatever linearity we have to do, we'll have to bring it back to our familiar case where we subtract any vector that we subtract the entire from the entire set, we subtract a vector which is there in the set, and then you will get a linear subspace, and then you can do analysis there. So most notions in, yeah.
So I have a question here. So like this x0 tilde, so that you get as a solution for x, ax tilde equals b tilde, right? So the solution set
Oh,
of
right. Yeah, this I have not written that, right. X naught tilde is a specific, or specific may not be the right word. Particular solution is more standard terminology. Particular solution to ax tilde equal to b tilde. Yeah. Yeah. So was that all? Was that the doubt?
yes, sir.
Yeah. So what is the dimension of this affine subspace for a system of linear equations with a solution?
The dimension of the vector subspace, right?
Yes. What is the vector subspace associated with it?
Null space.
The null space of A. Right?
Yeah. So what is the dimension of the null space? What is it called?
The nullity.
Yeah. So the nullity of the coefficient matrix is the dimension of the affine subspace defined by the solutions to a given system of linear equations with a solution. Can't be inconsistent. So the only thing that needs to be checked,
Nullity is equal to what? Nullity is equal to what?
Nullity is the dimension of the affine subspace. Just one. Dimension of solutions to ax equal to b. Solutions to x equal to b is an affine subspace. The dimension of that affine subspace is the nullity of the coefficient matrix. All right.
This solution space and the nullity space both are different, right? Null space we will calculate from the matrix and solution space with the augmented matrix, right?
Yes.
So the dimension of the null space will be the dimension of
Number of independent variables of the row reduced form of A. Number of non-pivot columns, you could say.
yeah, that will null space will be the dimension of affine subspace, right?
Nullity will be the dimension of the null space as well as this affine subspace, because the null space is the associated subspace to the solution space.
Okay.
So here, the dimension of the affine subspace is the dimension of the associated subspace. So in this case, the dimension of Ax equal to b, solutions to Ax equal to b, is the dimension of the null space of A, Ax equal to 0, which is exactly nullity. If you want to calculate this particular x naught, then you'll have to solve that system of equations.
Okay.
Now, the last concept, which is that of an affine transformation. If I have a map between affine subspaces, then first of all, we cannot expect the conditions to be of the form f of v plus w is equal to f of v plus f of w, because we don't even have the guarantee that v plus w will lie within that affine subspace. So what we need to do is what I was saying earlier. We have to bring this all back to the case of map between a linear subspace, and then we have to analyze it then. So if it is a function between affine subspaces, of course, there is an expression of this form. These are the associated subspaces to L and L prime respectively. And then I can add any element of L and L prime to get an expression of that form. So I'll take an arbitrary element and then I'll write L as V plus U. And I'll take F of V over here. These are expressions. So now if I have to define what is an affine mapping, then I go back to maps between U and U prime, where I can talk about linearity in terms of respecting the scalar addition, scalar multiplication and vector addition. So what I do is I take a vector in U and then I look at the following. F of V plus U. What is F of V plus U? Since V plus U is this, it is an element in L. V plus U is an element in L, small v plus small u. I take F of that will land in L prime. So V plus U is over here. It goes to something over here. But that something is of the form F of V plus some U prime, because that is the general element of the codomain. So if I look at this F of V plus U minus F of V, this is an element in U prime. And this mapping, if it is a linear transformation, then the original map F is said to be an affine transformation. So linear transformations are, affine transformations are defined in terms of linear transformations of the underlying subspaces. The only thing that you need to do to make sure is that whatever you translate the domain by, you have to translate the codomain by the image of that, so that when you go and come back, you're making sure that things are staying fine. And the last point is that affine mappings between vector spaces are translates of linear transformations. What does this mean? So affine. So if I have the entire vector space, just like I was saying that the entire plane is an affine subspace as well, right? So if I have something like R3 to R2, or let's just do R2 to R2 itself. Now I can talk about affine maps between R2 and R2, because these are trivial affine subspaces of R2 itself. If I look at an affine map over here, this will be always of the form T of here, let's say x plus y is equal to some x naught y naught plus T prime xy, where this will be a linear transformation. Just like affine subspaces were vector plus vector subspace, affine transformations between the whole vector space, between vector spaces, is a vector plus a linear transformation. And what is this exactly? This is just T of 0, 0. Because when I plug in 0, 0, this is a linear transformation. So T prime of 0, 0 will be 0, 0. So you'll just get this x naught, y naught to be equal to T of 0. So your affine transformations between vector spaces will look something like this. Generally, it will look like this. Since 0, 0 does not go to 0, 0, this is clearly not a linear transformation, right? The image of 0, 0 is 1, 3 in this specific example. While for a linear transformation, we always require it to be 0, 0. But this is an affine transformation. You can verify this by doing this f of v plus u minus f of v. You can check that this will be a linear transformation, because the underlying subspaces are what? They are again R2. Because since we are taking the entire vector space, we just have the representative vector affine subspace for the vector subspace is also again R2. All right.
So like generally in the questions they will give us the function f and we need to check whether it forms affine mapping, something like that, is it?
From affine mappings, there will be very few questions. I think this is a topic that is just for completion.
Okay. Because I'm
Uh,
not getting that last part you have explained. Affine mappings between vector space or translate of linear transformation. Like what
okay,
is P
so
prime, those terms?
okay, all right. So if I have a affine mapping between vector spaces itself, not these are not things which are proper affine subspaces. These are the entire subspaces itself. So I have some expression for T of xy. What do I need to check if I have to say that this is an affine transformation? I have to look at, so this R2, I can write it as 0, 0 plus R2. This is one of the representations as an affine subspace, correct?
Yes, sir.
So then the codomain, I can write it as T of 0, 0 plus R2. So this
Okay.
is domain. This is codomain.
Okay.
I'll just do this because that is how we go about checking that something is a affine transformation, right? So if I want to, if it is known that this is an affine transformation, then this T prime, which is again from R2 to R2, because the underlying, the associated vector subspaces are also the full spaces. How do I, what is the condition that this needs to satisfy? T prime of xy, which is defined as T of xy plus 0, 0. In this case, it is 0, 0. F of b plus u. I've used this representations. Compare with this.
Okay. Yeah. Okay. So
Minus T of 0, 0. This is a linear transformation, right? This has to be a linear transformation. Now, if I rearrange this, what I'll get is this itself.
okay. Okay.
So saying that T from R2 to R2 is an affine transformation is the same thing as saying there exists an x0, y0 such that this happens, such that T of xy is the sum of a linear transformation plus a fixed vector. And that fixed vector is actually T of 0.
Okay. 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 Got it. So it can be anything, right? Like the fixed vector and the transformation of the fixed vector in the this one will give, right?
That you could do, yes.
Yeah. Okay. Thanks.
So I have a question here.
Yes.
In this paper, they have asked the question 7th is related to some affine subspace question. So they have asked about the affine mappings between L and L prime. So if you could go to this question, it's in the
Where question number what?
7th.
The subspace is associated with a given affine space, is it?
Yes. Yeah.
Yeah. So what is the doubt?
So when do you check that this L, the subspace associated with the affine subspace, whether it's a line or anything? So should we be able to check whether there exists a function f of b plus u that takes it from
No, no,
L
no.
to L?
In this case, there is no talk of transformation, right? So let me just, I'll do one of the options maybe. Yeah. So the question is, let's say, what is the subspace associated with which option should I take up? I'll take the first one itself. Y is equal to x plus 1. So here you are not asked to check whether this is an affine subspace or not. Here it is just asked what is the vector subspace associated with this. So here there is no transformation, right?
Actually,
Here
sir, there is this
Yeah.
question six. Question 7 actually follows from question 6. So they have given L and L prime there, the two vector spaces.
Okay. Uh, okay. The subspace associated with, okay. Let me take L then. So L is given to be xy such that y is equal to x plus 1. Now this is essentially what we were doing earlier. So let's do two parts also if there is some confusion. So one is in R2 and one is in R3. So the first one, it is said that this is an affine subspace. Well, it is not said outright, but we can see that this can be written as 0, 1. So L, first of all, you see that it does not pass through the origin. So this is not a vector subspace itself. But take any point in L, any arbitrary point. Let's take 0, 1, for example. Any point of the any general point over here looks like x comma x plus 1, right? Points in L look like x comma x plus 1.
Yes. Yeah.
So if I subtract a fixed vector from it, what will I get?
X comma 1, x comma x, which
X
is
comma x.
yeah.
So the set of all points x comma x plus 1, which is L. Okay, maybe this I'll leave it as that. Now the set of all points of this form is the same as 0, 1 plus the set of all points of this form. Right?
Yes. Yeah.
So this is actually L. And here I've written it as some particular vector plus a subspace. So the vector space associated to this is just this, which is y is equal to x, or the span of 1, 1, whichever way you want to see it. Similarly, you look at L prime, take a particular point in L prime. Let me put x is equal to 0, z is equal to 1. So 0, we can put x equal to 0, z is equal to 0 also. Let's do that. This is a point in L prime. Is this fine? X is
Yes,
equal to
sir.
0, z is equal to 0.
Yes.
Now, if I take a general point, which is of the form x plus z minus 2z, and I subtract this point, what do I get? I get x plus z, z. So this general point in L prime can be expressed as the sum of this plus vectors from a subspace. You see x plus z, z, that is a vector subspace. So this L prime is this fixed vector plus, let me call it u2, where u2 is x plus z, z. And this is a vector subspace, is clear, right? What can you give me a basis or a spanning set for that vector subspace?
1, 1, 0.
1, 1, 0 and 0, 1, 1. Correct?
Yes.
Yeah. So that is the subspace which is spanned by those two vectors. So what I've done is essentially write the given sets as a fixed vector plus a vector subspace. So the subspace associated to L prime is U2 and the vector subspace associated to L is U. That must be there in the options somewhere.
So could you repeat the last part? Like, what did you ask about the span of the vectors?
Okay,
last
so
vector.
I just said that U2, the points in U2 are of the form x, x plus z, and z. So,
Yes. Mhm.
so this can also be written, it can be said that this set is just the span of 1, 1, 0 and 0, 1, 1.
Yes. Yes.
I
Yeah.
was just asking a spanning set for it. So
Okay.
the option could be this also, right? You should still be able to identify this as the same set, same
Mhm.
subspace. In this case, for example, option C, it is given xyz such that x minus y plus z is equal to 0, which is what the correct answer is. Why? Because y is equal to x plus z. So that is another way of expressing this set. So even
So
once you get the set,
so here y is equal to x plus z, right?
yes, y is equal to x plus z or x minus y plus z is equal to 0. So this u2 can also be written as xyz such that x minus y plus z is equal to 0. It is just a different way of writing the same. Okay. So next we have geometric constructions, lengths, angles, using a dot product. So the first familiar notion that we know is that of the standard dot product in Rn, wherein you can take the dot product of two vectors to get a real number. And this real number is related to lengths of vectors and angles. The formula for that is given over here. If you take the dot product of a vector with itself, that gives you the square of the length. The length of the vector is actually the positive square root of that. And the angle between V and W also, oh, here this is not theta, this is cos theta. So the cos of the angle between two vectors can be computed by doing V dot W divided by norm V norm W. Again, norm V norm W, these things are expressed in terms of the dot product. So if you have a dot product, then we can define a notion of length and angle. Generalizing this, the notion of a dot product, we get what is called an inner product. So an inner product on a vector space is a function which satisfies four properties. What are the four properties? Properties 2 and 3 are just that linearity of the vector space operations is respected, meaning in both coordinates. So if I have V1 plus V2 inner product with V3, then it is the same as the sum of V1, V3 and V2, V3. And since I was saying that we are looking for something like a generalization of the dot product, the first axiom or first condition actually just says that the length needs to be non-negative. The length, intuitively at least geometrically, you don't want the length to be negative. So the inner product, the requirement for the inner product is that the inner product of any vector with itself, which will be the square of the length that we will define, that has to be non-negative, and it can be zero only for the zero vector. Only the zero vector has zero length, everything else has positive length. And then there is symmetry. It doesn't matter what order you take the inner product in. This is an inner product. Now, the answer is the same. Now, this is very similar to how we abstractly define a vector space using the rules that we know for certain operations for vectors in Rn. Similarly, we looked at the standard dot product in Rn and just asked for a function which has a very small set of things that need to be satisfied. This could be redefined in some other way, and it will be done in particular examples. In certain scenarios, you will need a different notion of an inner product, and this is the most general setup. So this class of functions are interesting. They give rise to a notion of length and angle. Once again, length of a vector, which is again denoted using this two vertical lines on each side. This will be square root of VB. This makes sense because we have it to be non-negative. If it was a negative number, you cannot take the square root of that, at least in real numbers. And then you have the angle cos theta between V and W, that to be inner product of this divided by norm V norm W. But without referring to an inner product, one can define what is a length function. So the general notion of a length function in a vector space is that of a norm. An inner product was a function which takes two vectors as input and spits out a real number. But an inner product is just a function on the vector space, where given a vector space, I'll tell you what its length is. Strictly speaking, because of the first axiom, this is in R plus, but that's okay. We can take a bigger space and define it there and put that as an axiom that it has to be the length. It's a function which is always zero vector. And then the length of a scaled vector is the positive scaling of the vector, the norm of the vector. And then there is something called the triangle inequality. This is the triangle inequality. So am I audible? Is everything fine?
Yes, sir.
Yeah. I just lost network on the other device. Anyway, now given an inner product, now this does not reference any inner product, as you can see. It just says this is a function which satisfies these properties. But then if I have an inner product, then I can define this just like we get a length function from an inner product. It is exactly that. It is the positive square root of this. So inner product gives you a norm, but not all norms come from inner products. A norm, just if you want the length, you can work with a more specific function. So this is all about inner products and norms and so on. The rest of the content I did not have time to prepare slides for, so now we'll be back to writing. So this is, are there any doubts until now? Until this point, is everything clear?
Yes, sir.
Yes, sir.
You can think about things like how many vectors of a given norm there are. So suppose you have norm V is equal to 1 and V belongs to, let's say, span of 1, 1. The standard, if nothing is specified, assume standard. How many such vectors are there?
2.
2, 0, 1 and 1, 0.
It's not 0, 1 and 1, 0. It is 2. We need the vectors to be in the span of 1, 1, right? So those vectors will be of the form C, comma C. So it will be
1 by
1 by
root
root 2, 1 by root 2, and
1 by root
the negative of that. So the idea is that if you have a specific norm, it will be at a specific distance from the origin. Since okay, so if I have a vector, let's say in R2, what is length geometrical? It's just the length of this line. What does it say? The length, the distance between the origin and the head of the vector. That is your standard length. Now, any vector that satisfies norm of v is equal to 1 means that it is at a distance of 1 from the origin. What are the set of all vectors which are at a fixed distance from the origin?
Radius of a circle.
Yeah, so they are the circle with that given radius. Something like this, yeah. Now, if I also need that they are in a specific, along a specific line, then it will have to have, and it will have to be on this line as well as on the circle. So how many such points are there? There are 2 such points.
2.
There was nothing special about 1 and 1 comma 1. So you can just take v is equal to some k, and v is in the span of some v naught. As long as k is not equal to 0 and v naught is not equal to 0, the answer is 2 itself. Is that clear?
Yes.
So the number of elements in this is equal to 2.
Sir, these things we can imagine and plot only if we are considering standard dot product, right?
Yes, that's true. Yes.
Okay. If in the question they have given different dot products, then we need to write equations and solve this.
Okay, let's try to do that. So just using the inner product axioms, let us see if we can prove that the set of all vectors in a vector space such that this and v belongs to span of some v naught. Here you cannot take 1, 1 because it might be some vector space which is not Euclidean. What is this? So if you want to do something like this, what would be sort of the approach? What are vectors in the span? First of all, it needs to be in the span of v naught. So what would a vector look like? What would that vector look like?
Summation
C
ci
times V naught.
v naught.
There's no summation. There's just one vector, right?
Some C
Okay.
times V naught.
Yeah, then c times v naught. Yeah.
Yeah. So it's just CV naught. Any general vector would be of the form CV naught. So we have taken care of this condition. Now I also want that the norm of this CV naught is equal to 1. Right? But what is norm CV naught? What happens? How is norm CV naught related to norm V naught?
It's absolute value of C into V, norm of V naught.
Yeah. And this is a specific vector, right? This is a fixed constant number, this norm of V naught. So what I require is this should be 1 by norm of V naught. So you have 2 solutions, plus 1 by norm V naught and minus 1 by norm V for C. So the vectors which satisfy both of these conditions are V naught by norm V naught and minus V naught by norm V. And no other thing is possible.
Okay. So we can generalize for any inner product and
Yes. This particular question, yes, it is easy to see. But if it is something like the set of all points, it will not look like a circle. So if you want to have the geometric visualization, If you just say norm V is equal to 1, it need not look like a circle,
Okay.
right?
But can we perform these with operations with standard inner product, and whatever the answer we are getting, we can write for that?
In general, no.
Okay.
So just the fact that, let's say the statement is the set of all vectors with norm 1 lie on a circle.
Yeah.
That is true for the standard inner product, but it is not true in general.
Okay. Okay. Right.
So norm V square is equal to 1. What is this? This is just x square plus y square is equal to 1. Now you can see that this is a circle because this is the equation of locus of a circle.
Okay.
But if it is something like x square minus whatever, it's like minus xy1 minus, yeah, you can have something like axy plus 9y square, something like that you can have. This will not be a circle, right?
Yeah.
So
Okay.
whatever property for is true for standard is true for any other inner product is not correct.
Okay.
But yeah, in finite dimensional vector spaces, all norms are equivalent and all that is there, but that is not part of the syllabus. So I won't go into it more than that.
Okay. Okay. Got it. So in this
You
case,
have
we have
to,
to solve this equation and see how many solutions are here, right?
yeah, so you have to just use the 4 axioms
Okay.
and conclude,
Yeah.
because you cannot use the existing knowledge of things in Rn. The geometry might be different.
Okay. Got it.
All you know is these 4 are satisfied.
Yes. Okay.
All right. So now that we know what inner products and norms are, we have a way of seeing how two vectors, to the extent to which, so when I'm talking about length and angles in, or angles in Rn, if I have two vectors, the closer the vector is to the other vector, the larger the dot product is. Or at least if you normalize these vectors, it will be closer to 1 when you go over here, and it will be as far away from 1 as possible when it is orthogonal. So similar thing can be used to deduce linear independence. So coming back to a normal vector space with an inner product. Now you have a plus, a dot, and an inner product. None of them need to be the standard ones. You may have some abstract vector space with the plus, dot, and inner product given to you. In this case, so if it is in Rn, if I have to find, if I have to check whether this is linearly dependent. Suppose I have a bunch of vectors. I have n vectors. Is this linearly dependent or independent? How would I do? How would I go about doing it?
Check for orthogonal. Oh, like in general, yeah. C1 V1 plus C2 V2.
In general, you have to solve. You have to try to solve this system of equations. If it is in Rn, it will actually be a system of equations. But otherwise, you'll have to use something to see what are the possible C1, C2, Cn which satisfy this equation. When is it linearly independent and when is it linearly dependent?
When C1
All
C2 Cn
CIs, yeah, all
if 0 is the
Right.
only solution, then it is linearly independent.
Yeah, and if you have any one of them, if you have a solution with at least one non-zero entry for any Ci, then it's a linearly dependent set. So in general, this might be slightly hard to do. But in the case of the existence of an inner product, then you have a sufficient condition. Sufficient condition for linear independence is that Vi Vj, the inner product, this is equal to 0 for all I not equal to j. So why do I say, what do I mean by this is a sufficient condition? Can someone explain?
If this condition holds true, then we can say it is linearly independent. But if it is linearly independent set, then we cannot guarantee that VIVJ is equal to 0 for all.
Yes. So if VIVJ is equal to 0, then it is linearly independent. But if it is linearly independent, so for example, over here also, this V and W, they are linearly independent, even when they are not orthogonal to each other in the standard inner product space, R2. They are linearly independent, but this gives you a way of checking linear independence. So if you are given a set which is clearly orthogonal to each other, then you don't even need to go and verify all these equations. Then you can conclude that it is linearly independent. So how do we write it? Orthogonal sets are linearly independent. So what does orthogonal set mean? A set of vectors wherein if you take any two different vectors, they are orthogonal to each other. Orthogonal meaning their inner product is equal to 0. Now there is a more particular notion of orthonormal sets. I'll just write a finite set over here such that Vi, Vj is equal to 0 for all, or let me just write this as, are you guys familiar with this notation?
Yes, it's the Kronecker delta, right?
Yeah, but I don't know if it is introduced. So let me just write this as 0 for all I not equal to j, and Vi is 1. So not only are all the distinct vectors orthogonal to each other, each of them is of size 1. So this seems to be a lot to ask, right? An orthonormal set requires a lot of conditions to be satisfied. So there should be some payoff. The payoff is that the expression of any vector in that basis becomes easy. What do I mean by that? So in general, if I have a basis, if V1, V2, Vn is a basis, then we need coefficients of vectors. While you're doing matrix representation or anything else, you have seen that many times we need to know what the coefficients are. Coefficients of vectors. That is, how do I write V is equal to C1 V1 up to Cn Vn? I need to solve for this. This is once again a system of equations. Over here, this was a homogeneous system of equations. But here, if you want to express any vector in terms of a basis, you will get a system of equations. System of equations which is guaranteed to have a unique solution because this is a basis. But it is, you have to use Gaussian elimination and so on. If V1 to Vn is orthonormal, then Ci is just Vi with V, or let me write this V with Vi. So in terms of an orthonormal basis, so if you are given an orthonormal basis, if you somehow get hold of an orthonormal basis, what you can do is you can write every vector as just this. V with V1, V1, and so on up to V with Vn, Vn. So let's take maybe an example. An orthonormal basis for R2. The standard basis is also orthonormal. But let me take a non-standard example. First of all, is this an orthonormal basis? So if you want to check if something is an orthonormal basis, what are the things that you need to check?
That its norm is 1. You can check.
There are 3 things that you need to check.
Dot product is, inner product is 0 and the norm is equal to 1.
So first of all, let me call this, let's just call this a S. First of all, you need to check it's a basis. Then Vi, Vj is equal to 0 for all I not equal to j. And norm Vr is equal to 1. When I'm saying it's an orthonormal basis, then if this is actually satisfied, then C S as a basis is automatically given because it is linearly independent is given. Then you need to check that it is spanning or it is of the dimension of the space. Do you get why this is also required?
Just for implying orthogonality.
No. Orthogonality can be checked independently, and orthogonality will imply linear independence. But linear independence is not sufficient. I want a basis. So I need spanning property also, or the fact that the number of elements is equal to the dimension. We'll take another example of that sort also. If I
Because
just
it has to be
check,
minimal spanning set, right?
yes, it has to be minimal spanning set. So okay, so here are all these conditions satisfied?
Yes, sir.
Yes.
It has 2 elements. It is linearly independent because it is orthogonal. If you want, you can set up a system of equations and try to solve it. Each of them has length 1 is also readily verifiable. Once I have all 3 conditions checked, I know that this is an orthonormal basis. Now, how do I express, let's say, 7, 10 as, so let me call this guy as V1 and V2. Something times V1 plus something times V2. We have seen many times that we wanted to do something like this. We need to find the coefficients with respect to some basis, especially when doing matrix representation of transformations and so on. So in this case, it is just 17 by root 10 and minus 3 by root. So how did I get this?
By using the orthonormality property. Right? So
So I
C1
just
is
used,
V and Vi.
yeah, so I just took the inner product of the given vector with each of the basis vectors, and that happens to be the coefficient of that particular basis vector. Is this clear what was done over here?
No, sir. So last line.
Since this is an orthonormal basis, you have this expression, right?
Yes, sir.
Every vector V can be written as a linear combination of the given orthonormal basis, where the coefficients are just inner product of the basis vectors with the given vector. So here it is 7, 10 dot V1, which is this, times
Yes.
V1 plus what is the other thing? 7, 10 dot
1 by under
V2
root 2 minus 1 by under root 2 times V2.
times V2. But what is this dot? This is the standard dot product. So it will be 7 plus 10 by root 2, which is 17 by root 2
Yes.
V1 plus 7 minus 10, which is minus 3 by root 2 V2. This is what I just written there. And if this orthogonality or something was not there, you remember you had to set up a system of equations and then try to solve that system of equations. Here it is much simpler. But the thing is, we had to do work before. We had to get an orthonormal basis. So how do you actually get an orthonormal basis? So to see that, we'll do projections and Gram-Schmidt orthonormalization.
So I have a question here. Like, given an given a linearly independent set, so can we express any arbitrary vector in the span of that set in following this algorithm? Like, if we don't check it's an orthonormal basis or not?
That will
Is
not
it,
be true. No? So suppose your, let's say your basis is 1, 0 and 1, 1. This is clearly not orthonormal in the usual inner product, correct?
Yes, it's not even orthogonal in the sense.
It's not even orthogonal, yeah. So if there is orthogonal, there is a modification of this formula that you can use. You'll just have to divide by its norm. But yeah, let's not do that. Now let's come back to this. How do you express 1, 1 in terms of this basis? If you try to follow the wrong algorithm, this is the wrong approach. So what would you do? You do 10.11 times 10 plus 11.11 times 11. So if we were to follow this algorithm, this is what we would do, right? So we get something like 1 times 10 plus 2 times 11, which is clearly not equal.
Yes.
Even if I divide by norm and all that, this will not be equal. While I know clearly that it is actually 0 times v1 plus 1 times v2.
Yes.
Right? And unless you have an orthogonal vector, this first component will not be 0. Do you get that?
So if they're not, okay, yes, if they're not orthogonal, the first coefficient would not be 0.
Yeah, it would not be 0. Is that fine?
Yes, sir. So it's a stricter, it's more stricter in that sense that is a more stricter requirement that would require for
yeah,
the basis.
you require more conditions to be satisfied by your basis, and consequently, what you get will be very simpler computations for calculation of coefficients. That is one of the advantages.
Okay, but sir, if I were to define the inner product in the not the usual way, the usual inner product sense.
Okay.
Say I would devise the inner product in some ugly fashion, which is not the usual inner product.
Okay.
So would that still be the same thing and still not obey the same thing and the principles and algorithm fails
No,
there as well?
actually this up until this point we have not said anything about it being the standard inner product. That it could still be this expression holds for any inner product. The inner product need not be standard over here. If I am given an inner product space and an orthonormal basis with respect to that inner product, right?
Okay. So any generic inner product would follow this algorithm, right?
It would still follow this algorithm. You would do the inner product over here using that non-standard thing. And while you're checking for the conditions also, here orthonormality will mean with respect to that inner product.
Yeah, okay, I get it. Okay.
Yeah.
Okay, thank you.
In fact, this is just something really unnecessary, but since you asked, I'll tell you this. So if you are given, let's say, a basis, v1, v2, vn, let's just take a two-dimensional space. I have v1, v2. I can just define an inner product just by considering this to be an orthonormal basis. You can think about that statement if you want. Instead of starting with an inner product and then checking for orthonormal basis, I'll start out with the basis and I'll declare that that is orthonormal, meaning that this is of length 1. Both of these are length 1 and they're orthogonal to each other. And that will define an inner product because inner product has linearity properties, right? And
Yes.
everything is a linear combination of this. So your inner product essentially is determined by that.
Okay.
You get it?
Yes, sir.
Yeah. All right. Next, we look at projections. So here, why do we take this digression onto projections is that we have so far seen that orthonormal bases are important. But then how do I compute orthonormal bases? Like for the standard, let's say R2, R3, Rn in general, you have the standard basis itself. But if I'm given a vector space, let's say of the form X, Y, Z, such that, what was that thing that we used earlier? X minus Y plus Z is equal to 0. Let's just take that space from that example. Do you know an orthonormal basis for this exists for sure? So assuming that you're preparing something for the quiz, let me ask this question. Does every vector space have an orthonormal basis?
Yes, sir.
Yeah, can you say why?
You can start randomly at any place, and using Gram-Schmidt, you can keep discovery.
Yeah, so Gram-Schmidt is more machinery than we have discussed, but that is the idea. So that is where we are going to get an algorithm to get an orthonormal basis for any given vector space, starting from a basis. So the idea is to look at projections. So first we'll see projection of a vector onto a vector. On another vector. So this intuitively you can think of this as the shadow of one vector onto the other. So if you have something like V and W, so V does cast a shadow, right? So this let me call this projection of V onto W. So this is what is the projection of V onto W. Now, just using your parallelogram law, you can see that you look at some orthogonal thing. So let me use some other color. So this red vector is the projection. And similarly, this, if I consider these two red vectors, the vectors with a red arrowhead, what is the sum of those two vectors?
V plus W, right?
It's V.
It will be just V. There's no reference to W so far. So V is projection of this onto this plus some perpendicular vector, some vector which is orthogonal to this. So if I take V minus projection of V, that will be a vector which is orthogonal to W. Is that clear? So let me call this guy as V prime. V prime. V prime is orthogonal to W. This is the diagram and all that is there in R2 with a standard inner product, just for understanding the R2. Is this statement clear?
So it's almost like a Pythagoras theorem, right? If the diagonal element, the projection, you can decompose it into a projection and orthogonal to the projection.
I wouldn't call it The same as Pythagoras theorem. Pythagoras theorem talks about the lengths of it, but this is just a decomposition of a vector into its component in one direction and component in the orthogonal direction. So take for example, in the xy plane, if you have x comma y, you will write it as x comma 0 plus 0 comma y. So the similar thing you are doing, but you're not taking the axis as reference. You're taking w and its orthogonal and the vector orthogonal to it as reference and writing it this way. So if I start out with two vectors v and w, and I don't, they are not orthogonal. In this case, they are not orthogonal. But if I remove the projection of v onto the vector, what I get is an orthogonal vector. So v prime comma w is orthogonal. Is that okay?
Yes, sir.
So is there a confusion over here?
No, so it's fine.
Yeah. So you have v prime comma w to be orthogonal. So this is, you should always keep in mind that what we are trying to do is we are trying to go from a linearly independent set to an orthogonal set, which is slightly more than just a linearly independent set. And then we can normalize it and stuff and make it orthonormal. You can just divide by its norm to get a norm one vector. So, but we want orthogonality. When there is not orthogonality, we remove the projection to get the component which is orthogonal to the original vector. But can v prime be 0? When would v prime be 0?
When
the
it projects
vector
it to itself, right?
entirely on W.
Yeah. So
V belongs
when
to
is the projection of the vector itself?
when V belongs to W.
Yeah. So if I have a vector W and if I have a vector along it, the shadow that it casts is actually equal to itself and there is no orthogonal component. So that is not going to happen because we generally start out with a basis in which there are linearly independent vectors, which in particular means that there are no vectors which are scales of other vectors. So now you have, this is the first step of what is Gram-Schmidt orthonormalization. But what we have avoided is what is the expression for projection. How do I compute projection? All of this sounds nice, but what is projection of V onto W? This is just V dot W hat. This may not be the terminology used there. It's probably something like, okay, this is just a number times W hat. W hat is the unit vector in the direction of W. The more familiar formula is probably this. In the general inner product space, what you need to do is this times this. Is this fine? So what is the projection of an orthonormal vector? So I am given a vector W and I'm projecting a vector V which is perpendicular to W. Then what happens to the projection?
It vanishes, right?
Null vector.
It is a zero vector. So remember that projection of orthogonal vector to W is 0. And the earlier thing is projection of vector along W is itself. So if you have a vector along W, then its projection onto W is itself. All of this will be seen in a more formal setting later. Now this is projection onto one vector. Now what if I have a subspace? I can just using the diagram that we have seen, if I have a plane and a vector which is not on the plane, I can look at an orthogonal direction for the light to fall, and I can have a projection of that also. Once again, you see that all of these things, the thing that we have discussed, that projection of orthogonal vector to W is 0, and the projection of the vector along of vector along W. Okay, so it's to be read as, it's not projection of vector along W, it's projection of vector along W. Even if you have a vector along the plane, its projection will be itself. If there is a vector orthogonal to the plane, it will project onto nothing. So how do you compute projection of a vector onto
Sir,
a subspace W?
sir, what is projection of 0 vector onto W?
That will be 0 itself. Right.
Okay.
So there's nothing to project really.
Okay. Okay.
You could say that it lies along W. So
Oh, okay. It's 0, right? Like the projection.
yes, yeah. Even if you just put V is equal to 0 over here,
Okay.
you'll get 0.
Okay. Actually, in week 8 graded assignment, there was a question like it's given that for any subspace W, there exists V belongs to V such that projection of V onto W is minus V.
Is week 8 grid assignment deadline done?
Yeah, it's done. Graded assignment 8. It's done.
Just one moment.
Yeah.
What was the question?
Question number 3, option number 2.
The 3 might not be my 3 because just one moment.
Let V be an inner product space of dimension n given a subspace W belongs to V of dimension k.
Maybe we'll discuss that after I discuss the projection transformation.
Okay, sure. Because in that second option, like I thought, we can substitute V as 0, then projection of 0 onto W will be 0, so that becomes minus V, right? Actually, I took V as 0, and then since it says there exists, so V can be 0, right? Like if at least one is true, the statement has to be true.
Just one moment.
Sure.
Yeah, you're right.
Yeah, actually, I marked it as true, but it.
Okay. Okay, we'll see. We'll correct that. It has to be a non-zero, but yeah. So if it is non-zero V in V,
yeah, then it's false.
Yeah, then it's false. Yeah.
Okay, thanks.
This just remind me to get this fixed. Maybe just write to me. Yeah, let's see. I'll talk to people.
Yeah, okay, sure. Thanks.
Okay. Where were we? So projection of a vector onto another vector is done. Now, how do I project a vector onto a subspace? Now, every subspace has a basis. Now, suppose there is an orthonormal basis. I'll write ON, basis of W. W1 up to WK. Now, if I have a basis of this form, now don't ask me how I got the orthonormal basis, but just assume that we have one for now. How do I compute projection of V onto W? It is just summation of projection of V onto the basis elements. Now, you know how to do it for individual vectors using that formula. And in this case, you have even an orthonormal basis. So the projection of V onto W1 would just be V dot W1, the inner product of V dot W1 with times W1. This is nothing but V dot W1 dot W. Right? So now we know that given a subspace, how to define the projection of a vector onto that subspace. Which means I can given a subspace, I can define this map P of W from, I'll write it as V to V. We'll see what happens. So PW of V is nothing but projection of V onto W. Do you understand this map? I'm given a subspace W. And what I do is take all the vectors in V, and the image of V is just the projection of V. You can check that this is a linear transformation. What are the properties of this? What is the kernel? So whenever we talk about linear transformation, we look at kernel and image. That is the first thing that we need to look at. What is the kernel of PW? What are the vectors which projected onto 0? Keep in mind the example of the line and the plane. So what are the vectors which project onto 0?
0 itself, right?
0 itself is there, but that is not all.
All vectors perpendicular to it.
All vectors perpendicular to this line in this case. If W is the plane, it is all vectors perpendicular to this plane. So all vectors perpendicular to all vectors in W, which is called W perp. So it's V in V such that inner product of V with W is equal to 0 for all W in W. So you look at all the vectors which are orthogonal to every vector in W. It is enough to check on a basis, it is enough to check on a basis. So what happens then when you compute quantities like this, V comma W1, then it becomes 0. And the sum also consequently becomes 0. Right? What is the image of PW?
W, sir.
Is this clear why? Because look at this element. Like if you just want to look at the formula and deduce, look at this element. They are linear combinations of Wi's. So it's definitely going to lie in W. And even if you want to look at it at the intuitive way, which is not a proof, but still something to think about, it's like the shadow which lies along the thing. So the projection always lies in the space. As a consequence of these itself, you'll have that this is equal to this. Okay. There's one more thing needed, that to say that for any W in W, PW of W is W. So if I take a vector in the subspace and I project it onto that subspace, then I'll get the vector itself. So all of these things are in specific cases. We saw that this was easy to see. Projection of orthogonal vector is 0. Projection of vector along the vector is itself, and so on. Now this happens in general for any subspace as well. Now once I have these properties, I have this is equal to this. So what does PW square mean? It is PW, the transformation, followed by itself. So I can go from V to V, and then I can take the image and then apply the transformation again. So that is what PW square is. So if I take a vector W, if I take a vector V and then do PW of V, I get some vector in W, right? Because the image is in W. But then if I do PW of V, which is I take the image of V and then apply the transformation again. This image, it's already in W, and vectors in W don't change. So what do I get over here? This will just be PW of. 'V. Is that fine?
Yes.
So PW square is PW. Is there any other property that I'm missing? That's it, I think. Kernel image square. So, okay, can the projection be an isomorphism? Let's just say this. Let's just see this. When is the projection an isomorphism? Is it possible?
It is not possible.
It is possible in a very trivial case where you take W equal to V. If you take W equal to V, you are not really projecting onto a smaller space. So everything remains the same. So this becomes an identity transformation. That is the only case where it is an isomorphism. Yes, but only for W equal to V. If you have any subspace which is not proper, which is not the entire space, what happens? What does rank nullity tell you? Dimension of kernel plus dimension of image is equal to dimension of V. This is what your rank nullity theorem says. Now, what is kernel of T? I called it W per, right? And what is this? What is image of T? Here T means PW. Image of T is just W, right? Now, if V is not equal to W, then dimension of V minus dimension of W is some number, is some positive integer. So your kernel will have some dimension, meaning that this can never be injective unless V is equal to W. Is that clear? Is this fine?
Yes.
Kernel of PW is not equal to 0 unless W is equal to V. Because see, these are the properties of projections. Now, we have used in many places, if we have a orthonormal basis, then this is how we do things. This is what we have been saying. But how do I get an orthonormal basis for a given vector space? So suppose B is a vector space, B is a basis. We don't assume that B is an inner product space and B is a basis. We use the same observations that we saw earlier to get an orthonormal basis from B. So what we do is, first of all, we need all vectors to be of unit length. So we take the first vector, let me call this guy U1, and I divide by its norm. So what is the norm of U1?
It's 1.
Yeah, norm of U1 is 1. So next, so the V1 could have been something longer or shorter. So we have normalized it so that it is unit vector. But the second vector, for example, is V2. This need not be orthogonal, and we want the second vector to be orthogonal. We want each vector to be orthogonal to the other vectors. So what we do is you write u2 tilde as u1 minus projection of v2 onto u1. So what happens over here? What you get is a vector which is orthogonal to u1 by construction. And then
Sir, it is V2 minus projection of.
oh right. Sorry. Yeah. v2 minus projection of v2 onto u1. Yeah. So first you remove the component that lies along the first vector and then normalize it. That's how you get the second vector. So what do you do for the third vector? So for u3 tilde, you take v3 and you subtract its projection along u1 and subtract its projection along u2. So at each stage, what you're doing is first making it orthogonal and then normalizing. And so on for n steps. Yeah, there are n vectors, so n steps. This u1, u2, un is an orthonormal basis. So if you have a basis for a vector space, then you'll have an orthonormal basis just by following this procedure. And you always have a basis for a vector space. So that concludes Gram-Schmidt procedure. Problems for each of these things will be taken in the TA sessions. There is one more topic, which is that of orthogonal transformations. I'll quickly sum up the results that are there over there. Now, just like we defined linear transformations as functions which respect the plus and the scalar multiplication, the dot. Here we have an additional structure now. So it is natural to look at maps which respect that structure also. So this is a linear transformation, which means it already respects plus and dot. And in addition to that, we have the following property. The inner product of two vectors, both of these are inner product spaces. It's probably from V to V itself. T of V, T of V prime. So here, what happens as a consequence? What can you define using the dot product? The lengths and the angles, right? So this is a length and angle preserving. Length and angle preserving linear transformation. But in general, it preserves inner products. It does not matter if you take the inner product of two vectors or if you take their images and then take the inner product. The number will be the same. So it has properties like it preserves lengths and angles for all V prime in V. Orthogonal transformations preserve lengths and angles. So before we go ahead, is an orthogonal transformation injective? What do you think?
Yes.
Can you give the reason why?
Because intuitively it is the same subspace which we are either rotating or something.
Well, rotations are particular examples. I'm saying in general, if lengths are preserved, then kernel has to be trivial. Kernel cannot have any non-trivial element. So what would be an element of the kernel? What is by definition an element of the kernel?
T of x is equal to 0.
Zero vector space.
Yeah. If V belongs to kernel T, then what is the length of V? By definition, this has to be equal to what? Since this is an orthogonal transformation.
T of V, comma T of
T of V, T of V. But what is T of V since it is in the kernel?
0.
This is
V,
0.
right?
So if the inner product of V with itself is 0, then what is V itself?
It's
Has to be
trivial
0.
0.
So the only element in the kernel is the 0 vector. So it's injective. Is it an isomorphism?
Yes, sir.
Why is it an isomorphism?
It is from V to V.
Yeah, so it is from the same space to the same space. So yeah, just give me one more statement. Why is it an isomorphism? It is from V to V. You can have in general maps from any set to another set which is any set to itself which is injective but not surjective, right? But in the case of linear transformations, because of one result, it will always be injective if and only if surjective if the spaces are the same. And what is that result? Any guess? We discussed this in yesterday's session. It's rank nullity theorem. So if your dimension of kernel of T is 0, then dimension of image of T has to be dimension of V. And since V is the image also, so there is full image. Is that clear?
Yes, sir.
Orthogonal transformations are isomorphisms.
but it is always under the condition that dimension of domain is dimension of range, right?
So here, orthogonal transformations we do define from space to itself.
Oh, okay. We can't define from V to W, is it?
We can, but then it will be something like an embedding.
Yeah, correct. In that case,
Yeah.
it cannot be isomorphic.
It need not be. Yeah,
Yeah.
it need not be.
Okay.
Yeah. But injectivity is definitely will follow. Because injectivity here, it doesn't appeal to the fact that it's in V. So, right, so then examples and all that you can check from the lecture videos. Matrix of an orthogonal transformation. So this is what is called an orthogonal matrix. Matrix of an orthogonal transformation with respect to the same basis for the domain and codomain. It's an orthogonal matrix. A such that A transpose is equal to A transpose A is equal to identity. So here you see that it is one more way of seeing that it is invertible map because the matrix of the transformation is invertible, meaning it has no nullity and it has full rank, which will translate to the transformation being injective and surjective. But yeah, so if I take an orthogonal transformation and compute its matrix with respect to the same basis for the domain and codomain, the matrix that you get will be an orthogonal matrix, meaning A transpose is equal to A transpose A is equal to I. What does A transpose is equal to A transpose A is equal to I simplify to is A has orthonormal columns. Do you understand this statement? A has orthonormal columns. So each column of A has length 1 and they're orthogonal to each other. So if some matrix is known to be an orthonormal, an orthogonal matrix, and then some entries are given, sometimes you can deduce some other entries just by using the orthogonality of the columns and the fact that the columns themselves have to be of unit length.
So rows are also not orthonormals.
Yes, because A and A transpose, A transpose is also an orthogonal matrix, right? Because then it becomes just A transpose A times is equal to A transpose is identity. So if I have, let's say, 1 by 10, 2 by 10, I'll just do something like this, and K, and some entries. So what could K possibly be? There could be something like questions like this. And or how many possible values of K are there? How many possible values of K are there?
2.
Yeah, 2. So the fact that it has to be of unit length will force 1 by 100 plus 4 by 100 plus K square is equal to 1. That's just the definition of length of the first column is 1. But then you have K square equal to some number. And so you'll get plus and minus. Did you follow that argument?
Can you explain it once, this argument?
Yeah, okay, so this is C1. Suppose it is known that this matrix A is orthogonal. If it is orthogonal, then its columns are of unit length and they are orthogonal to each other. So we are not worrying about the other columns. There could be something there also where you'll have to first get K and then find some other alpha, something over here. Maybe that you have to use orthogonality for this. For this, I'll just use the fact that the first column is of unit length. So I need 1 by 10, 2 by 10, K equal to 1. So what does this mean? 1 by 100 plus 4 by 100. I'm squaring the things is equal to 1. This is forced. So K square is equal to 95 by 100, which implies that K is plus or minus square root of 95 by 100. Either of them work.
Sir, to construct this matrix from orthogonal transformation, are we required to take only orthonormal basis to get orthogonal matrix, or any basis will do?
Just one moment. The matrix of an orthogonal transformation with respect to an orthogonal basis is definitely orthogonal. Just one moment. How about we do it with an example? Whenever you have doubts, do examples. So take R2 to R2. What is the simplest orthogonal transformation? It's just the identity transformation. That's an orthogonal transformation. It preserves lengths, angles, it preserves points. So now if I take something like, but there it'll be fine. There you'll get an identity matrix itself. Yeah, I'm not 100% sure about this. Since it is the same basis for both sides, I think any basis will work. So why do you think any basis won't work?
No, like while solving problems, I just checked. So every time we take either orthogonal basis or orthonormal basis. So I was not sure.
Right. Yeah, I'll think about it and I'll tell the TA to address this in the next session. I'm not 100% sure, so I don't want to give out the wrong thing. But if you use orthonormal basis, the same orthonormal basis for both sides, it is definitely an orthogonal matrix.
Okay.
If I have any basis, I'm not sure. I'll just verify that and I'll give you a definitive answer by tomorrow. In
Yes.
tomorrow's session, I'll address that. Yeah, nice question. So for now, let this be with respect to an orthonormal basis. Maybe this will be extended. But okay, this point is clear, right? Like how to find missing values when certain things are given. What is the property that needs to be used? And there are examples, rotation matrices, rotation in R2, rotation about axis in R3. Some nice examples are given. So you can go through that as well. And that brings us to the end. Yeah, if there are no questions, you can leave. If you have specific doubts, yeah, please speak up.
So I have a specific doubt regarding the same quiz paper in question number. So I don't remember it. Just
I don't have the link to it anymore.
Okay. I'll just paste the link again. Here it is.
Yeah, what is the question number?
The question number 11. So
With respect to the user product and ABC. Okay.
so here the
gamma is defined before, correct?
Okay, is gamma defined before?
No, beta is defined before. Beta is from a previous question.
Oh, I see. So I was kind of confused. Like, from where could I get the beta? So I started on with the standard basis.
Yeah. It is a comprehension question which starts with question 9, I think.
Okay.
Yeah, question 10 tells you what is beta, as in it asks you what is beta.
Okay. Now I get it. Okay, it's right. Thank you.
Any other doubt?
Sir, I had a doubt under the projection formulas. As for
Okay.
the denominator, is it norm square or norm?
It is norm square. Which one? It is this one, right?
Even if it's orthogonal?
It is orthogonal to what? No, this is the general formula for projection of V onto W, whatever that W may be. We are not going to project onto a zero vector, so the denominator will never vanish.
Okay, sir. Okay.
Any other doubts?
So
There is also just one moment.
Yeah.
Maybe you have seen it this way. It's the same. Yeah. Okay. Yeah. Go ahead.
Yes, like that graded assignment problem is should I write to support or it's fine?
It is support that has to fix it, but yeah, maybe make a discourse post and tag me.
Yeah, sure.
I'll forward it to the people responsible for it. Yeah.
Yeah.
So that's in the third question, right, Girish? So I also found that the projection should be the zero vector itself, the zero itself. So there it was marked incorrect for some reason, and then I was
Which one? Which one?
the third question that
Yeah,
Girish was
third
asking.
question, second option.
Yes.
Yeah, it is correct as it is stated, but the intent was to probably give there exists a non-zero vector.
Yes.
Okay. All the best for the quiz then.
Thank you. Thank you.
Let's wrap up.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
And by the way, there was some issue with week 7 grades showing.